All right, cool. I see. Maybe let's keep it on. Okay, let me just slowly start by remind everybody where we stopped last time and what the plan is for today. And then I think only 9 people are going to join in a couple of minutes also. Okay. Perfect. So what is our goal? So remember, so we are studying. So we have x pi, which is going to be a weighted three-dimensional simplicial complex. And again, just to remind you, so x is going to be x0 union xd. So xd are all the top level spaces of size d, and sort of go down by inclusion. And pi is also the distribution over these spaces. So pi 0 up to pi d. And again, pi d is some arbitrary distribution on top level faces, and we just push it down by this sort of random sampling process that we discussed several times. And basically what we are interested in asking, when is such a complex an expander? In particular, we're looking at this notion of local spectral expander. So the definition is that x pi is a local spectral expander, and there's going to be a parameter gamma. So this is gamma local spectral expander. So just say LS for now. If basically, for any link, its graph is a gamma expander. Okay. So we go from faces 0, 1, 2, 3 up to d minus 2. And so then the vector for every k, which is at most d minus 2, for every face tau in xk, the underlying graph for x tau is a gamma expander. So the underlying graph of it is, or equivalent to the complex is, because this is just a recursive definition. Okay, and then the main thing we're proving is the trickling down theorem by Oppenheim that said the following thing, that if you want to guarantee that actually a sufficient condition is that all the top level or the maximal graphs, the one for case d minus 2, are gamma expanders, and also all the bottom ones are just merely connected. So again, we just write the theorem. It says that if two things happen, so again, that x pi is also going to be this d-dimensional thing. Don't keep repeating it. So assume two things. So one is that for every tau in xd minus 2, the underlying graph is a gamma expander. Notice that when tau is a d minus 2 phase, x tau is actually a graph. There's nothing more than a graph, right? You have like nodes which correspond to sets of size d minus 1 containing tau, and edges that correspond to sets of size d containing tau. That's it. So x tau is really just a graph. So this is being a gamma expander is just a property of graphs, nothing more than that. And secondly, that for every k at most d minus 2, and for every tau k, x tau is connected. The underlying graph of it, the graph of x tau is connected. And the conclusion was that then x pi is a gamma over 1 minus d minus 2 gamma local spectral expander. So why is this called the trickling down theorem? Because you start with the top level faces being really good expanders, and you trickle down the expansion so that lower level faces are also very good expanders, as long as you know gamma is sufficiently small compared to this. So this is why it's called the trickling down theorem. It trickles from the top level faces to the bottom level faces, and it sort of slightly degrades. Later, next week, after, we're going to see a different phenomena where actually things improve as you go down in the complex. If you assume something stronger about the top level faces, or in general about the complex, but for now, this is going to be a starting point, saying that if the top level faces or graphs are expanders, you can trickle down the expansion all the way down to the bottom and you don't lose too much. So what did we see about that? So we saw two things. So we saw that it is sufficient to prove it for d equal to 3. Right, so if you remember, there was this inductive proof that said, well, if d is more than 3, then you can, by induction, prove this thing for the links, the one links, and then just because the complex truncated to the third level, just apply this for d equal to 3. So again, I won't repeat this, but this is a very, very simple proof. So really, all of the difficulty is in the d equal to 3 case. So for d equal to 3, what do you want to prove? So just to repeat that. So what is the d equal to 3 case? Just so we read it explicitly. So x pi is going to be a 3-dimensional weighted complex. We assume two things. One is that for every node v in x1, xv is a gamma expander. So the underlying graph of it is an expander. Again, the 3-dimensional case, the good example to keep in your mind is that you have a graph of triangles. You have triangles and edges and nodes. And then you say, well, for every node, look at its neighborhood of edges of triangles. Think of that as a graph. This graph is going to be an expander. So that's one thing. And the second thing was it's x, like the underlying graph. So the graph of x. So just say nodes and edges, ignoring triangles. It's connected. And the conclusion would be basically the theorem d equal to 3. So the conclusion would be then x is a gamma over 1 minus gamma expander. So the local spectral expander. But what this really means is that the underlying graph of x is such an expander. But all the other graphs we assume they're already even better expander, like gamma expanders. So we only have to prove that the underlying graph of x, merely by being connected, and because all of the one links are expanders, this graph also has to be a really good expander. So this is like a really surprising phenomenon that happens here. And later I'll actually later show you why we have this connected assumption, why this is like a natural assumption to make here. But we'll discuss this once we see the proof. Okay, so this was just a recap of what we're trying to prove here. Any question on that so far?
I have a little bit of a higher level question, I guess.
Sure.
I think I get the connection between these global and local spectral expanders, but at this point, should we have a lot of intuition, if any, for why a good spectral expander is a good like the connection between the eigenvalues and the actual expansion of these objects?
No,
Okay.
you shouldn't. Partly because we haven't seen it really. I mean, one thing we are going to see starting today, that when we come to analyze random walks in this graph, which is much more like again, it's not quite as a edge expansion property, but it's sort of related to it, is connected to this type of, being an expander. And I think it's really reasonable to ask about edge expansion. I don't know, Max, do you know of any reasonable definition?
So I would say this is a very good question. And the answer is that it's way more complicated than on graphs and that you should not have intuition for it. And that I think pretty much no one has intuition for it. And what is known, in fact, is that the spectral properties do not imply the kind of edge expansion properties like you have on graphs. So like the Cheeger inequality, I think works in one direction, like edge will give you spectral, but spectral does not give you edge expansion in the same way. So the extensions to kind of edge expansion and Cheeger constant style definitions are topological HDX, and they are not equivalent to spectral HDX. So things kind of break down at higher levels.
So local spectral expanders doesn't give you topological overlapping property?
No.
Okay.
The topological overlapping property, I think the weakest we know is cosystolic expanders give you topological overlapping. Okay.
Yeah, so let me just explain this notion. So topological overlapping is a phenomenon that people observed in geometry. I might explain later, but then the big realization in this area came by Gromov maybe 20, 30 years ago when he realized that actually this follows from a topological property, not a geometric property. Again, these are all buzzwords for now, but it came from some connection to topology, and this turns out to be the analog of that, maybe the Cheeger constant or edge expansion. I'm not sure how to view it. Some analog of that. And yeah, like I don't know enough about this connection. But I think people don't know enough how this actual notion of expansion is connected to this topological. So this other thing that Max was talking about, this cosystolic expansion, is another type of not topological, but I would say yeah, it is sort of topological. It's a different notion of a topological definition of expansion that is connected, but it is not clear what its connection is to local spectral expansion.
I think the claim is that cosystolic expansion, I've never actually seen this result, but Tally has claimed that cosystolic expansion implies local spectral expansion, but the other direction does not hold. It's not actually clear to me that this result is anywhere in the literature, but this has been claimed to me by a reputable source.
Yeah, so you see there's a lot of unknown here.
So the main motivation for focusing on this definition is its application to random walks and stuff like that?
Well, no, it's because it's easier to work with. I mean, it's easier to prove things on it. You can prove that that your HDX is a good expander in that sense by just analyzing its top level faces, which is in practice much easier to do because they look simpler. This is not clear now, but you will see it in few lectures. It's an example. Yeah, but no, I want to emphasize, I mean, there are applications of expanders where it seems like so far you need different definitions. Like this definition gets connected to analyzing Markov chain Monte Carlo algorithms and so sampling. But for example, for quantum codes, that is another application you could have. It seems you need a different type of a notion of expander, like some notion of a topological notion of expander. Whether this is enough, I don't know. It's also not clear how to construct these graphs or these complexes later. So I'll tell you more about this later once we finish the proof. But there's more unknown than known, I would say. This is like a very much open area, I know, being actively studied now, which I think is why it's exciting, right? I mean, there's so many things to discover. Even understanding what is the right definition of expansion. It's unclear. There are like 4 or 5 different definitions, and some imply the other, some don't, and it's not clear which one is good for which application yet. But slowly, people are discovering things. Any more questions? Okay. So now let me remind you of this lemma that we saw last class. That's sort of this technical lemma that will be the main driving force behind this proof. So let me first show you some definitions, or call it the definitions from last time. So again, now we're just going to be talking about, so again, let x pi be a complex again. And so we need 2 definitions, or 3 definitions. So one was this definition of function classes. So ck of x is just a space of all functions from xk to the real numbers, all real valued functions on the kth level of the complex. And we endow it with a distribution coming from pi k. So given a function here, we said its expectation is just going to be the sum of all tau in xk, then tau distribution over the space, f tau. And also, you can use the define inner product. So given F and G. In CK, the inner product is just the expectation of F and G. Okay, so we've seen this expectation that sort of play nicely with the way we define our distributions. And we needed, so again, two definitions about links. So for simplicity, let me just, okay, let's do it in general. So given a phase tau in xk, where k is most d minus 2, so we needed two definitions. So one definition was just a tau, which is the adjacency matrix. X tau. So we look at the complex of this link, and we look at its nodes and its edges, endowed with the weights on the edges coming from pi. And this defines the adjacency matrix. So we've seen, I'll repeat the definition later once we need it. Oh, but actually, what do we need the definition? We need some properties of it. So one thing, so this was one thing we need, and the other thing we needed is this notion of, again, so given a function f in, let's say maybe C L of x, we're going to define f tau in CL of x tau. So again, it's in L sets that are in the link of tau. So they come from k plus L sets in the whole complex. So this is only defined if k plus L is at most d. And it's just defined to be the value. So f tau of phase sigma is just f of sigma. So this is sort of like a type of a restriction. So we just look on phases where sigma union tau is a phase in the whole complex. Okay, so this was something that we called localization. And we're going to see a different notion come up later called restriction that is going to be somewhat similar, but not quite the same. But so we're going to give it a different name. This is called localization. And so what was it? So this was this local views. And again, for our case, we only care about tau being just a vertex, right? That's going to be the only case we're going to care about for this proof, but we're going to use these definitions more generally. So what do we know? So what did this lemma say? What we proved last time. It said that if I want to look, so again, let me just specialize to the case where we're in a three-dimensional complex. That's all that we're going to need. So x pi is going to be a three-dimensional complex. And we're going to take two functions, f and g, b. Actually, somebody, it was noted in the piazza that we made some mistakes, I think in the notes, but the order in which we choose, oh, actually, maybe not. Maybe for what I want to say now, it's fine. This works in this generative. So, and let's choose f and g, the functions in C1 of x. Then we're going to look, so these are so f and g are two functions on the nodes of x, and we want to understand the inner product. And the claim is that this is going to be the average of the inner product of f and g when you're localized to one links of the complex. That's going to be the expectation of v in x1. Again, v is sampled according to pi 1 of what? Of the localized version of f in the localized version of g. Okay, so we've seen that last time. And it comes from basically exchanging orders of summations. So we've seen the proof last time. There was one claim, and the other one said that if I look at the action of the graph AFG, that's just going to be the expectation of, again, same thing, v in x1, v, fv, g. Okay, so both for just the inner product of f and g and the inner product of af and g, you can just move to these local versions. Okay, so I wanted to put a proof. It was somewhat of a technical proof, but it then just amounted to order, like summing things in reversing order of summation and using properties of the distribution pi. That's the way it sort of also trickles down in the complex. And now I want to show you how we can use this lemma to basically prove Oppenheim theorem. But maybe before doing that, are there any questions on this lemma about any of the definitions in this lemma?
It's maybe worth noting the issue that Mohit brought up in the proof had to do with considering these faces as kind of ordered versus not ordered, like the edge VW. Because normally we think of these things as unordered, but then some of the expectations didn't make sense as defined. And so I guess we'll fix this in the notes, but really kind of what's going on is that this is basically shorthand for just writing out kind of a symmetrized version of the sum over all possible orderings. And then all of the different symmetrized versions, the ordering doesn't matter at all. So all the different symmetrized versions end up being exactly the same. So we kind of just shorthand write them as one. But really every time what's going on is we're kind of writing a symmetrized version out over everything.
Yeah. Yeah. So maybe just to clarify that if at any point we write something like the expectation of VW in X2, so we're really sampling a pair V and W according to phi2, but then deciding which one is V, which one is W, we just put, in this case, the two options are equally likely. If it's 3, so 3 factorial and so on. Yeah, but we're going to fix it. It's a good thing that you noticed it. Yeah, so we're going to fix this in the note. So that was a good point. Anyways, I'm not sure if that issue is actually going to come up in the proof of Oppenheim theorem, but it was an issue in the proof of the lemma. Okay. So now let's go to the proof of the lemma. So what do we want to prove? So again, so let me remind you. So again, we have x pi, which is a 3-dimensional complex, and we assume. So and we assume that for every v in x1, xv is a gamma expander in the graph sense, and also graph of x is connected. And our goal is basically to prove that x is going to be a good expander, right? So what does it mean to be a good expander? So we want to use the Rayleigh quotient. So I want to show. So what is to show that x is a gamma over 1 minus gamma expander. Again, the underlying graph of x. So graph of x. And we're going to use the Rayleigh quotient to do that. So what do we want to show? So using the Rayleigh quotient, so viewpoint, we want to show that for every f in C1 of x, so function of the nodes of x, that is orthogonal to the O1 vector. F transpose AF over norm of f squared is at most gamma over 1 minus gamma. All right, that's our goal. And so it makes sense that to do the f is maximize this quantity. So let f be the eigenvector of lambda 2, I guess, of A. So that's going to be the maximal. That's going to maximize this quantity. And also let me just assume that the norm of f is 1. So our goal is just to bound f transpose AF. So we want to bound lambda 2, which is just f transpose AF. And A here, I mean, if it's not clear, A is the adjacency matrix of the graph of x. And to begin with, what do we know? So because x is connected, what does this tell me about lambda 2? Anybody? I have a graph. Always the first eigenvalue is 1. What can you tell me about the second eigenvalue if it's connected?
Less than 1.
It's less than 1. Yeah, it is less than 1. That's all that we know. It cannot be 1. A second eigenvalue of 1 only comes if the graph is not connected. So it's just less than 1. That's all that we know. But somehow we want to bootstrap the information on links and get this sort of much, much better bound. That's what we're going to be surprised. So how are we going to do that? Well, let's do that. So let's see. So with F transpose AF, it's the same as, so lambda 2 is AFF, right? The same as F transpose AF. And now we're going to use the first property of, or maybe the second property of the lemma. So this is just going to be the local expectation over nodes V, next one, AV, FV, FV, right? That's a natural thing to do here. We know we can move to links. We just move to links. We know that AV is an expander, so we want to use that somehow, right? That's like the natural thing that we want to do once we've seen this Garland's lemma that allows us to move from global functions to local functions. But what do we know about FV? F we know is orthogonal to the O1 vector, right? But we don't know that for FV. FV might not be orthogonal to the 1 vector. So that what we want to do is say, well, FV is just a localization. Just you keep some of the values of F and the rest you set to 0, right? So just some subsets of the nodes of F. So it might not sum to 0, so we want to decompose it. So let's decompose FV to be the parallel part plus the orthogonal part, where the parallel part is just going to be FV in a product with the 1 function on V, just the 1 function everywhere, times 1V plus, maybe that's it. And FV perp is going to be the difference. So the same thing that we've done for graphs, we're going to do it here again. And the point is that the parallel part of the FV doesn't have to be 0. Well, if we sum all of them, they're going to be 0, but each one individually is not going to be 0. So let's see, what is AVFV? Now we're just talking about graphs. So what is AV? So this is adjacency matrix of, FV parallel. So remember that we said that, AV, an eigenvector of any adjacency matrix of a weighted graph, the way we view it here on the right is just that the 1 vector, constant vector, is going to be an eigenvector with eigenvalue 1. So this is just going to be FV parallel, right? It's just a parallel part. If I act on the perpendicular part, well, it's going to be still perpendicular to 1, right? So it's going to be, it's going to be 0. So it's going to move the parallel to parallel, perpendicular to perpendicular. And also because it's an expander, so far this is just properties of being a graph. But because it's an expander, because AV is a gamma expander, we know that AVFV is L2 norm with at most gamma FV, right? And now we want to use these 3 properties to analyze this expression of AV, this expression here, right there.
It should say FV perp. Is that right, Shahar? On the
Where? Oh yeah, I'm sorry, you're correct. My mistake. Perp. Thank you. Perp. The perpendicular part. Yeah, thanks. So it's everything orthogonal to 1. Shrinks down. Cool. Okay, so now what do we do? Now, well, let's just analyze this. So what is, so we're going to the expectation. Actually, let's do it. So what is the expectation over V? And I want to keep it say V next one. V is always going to be next one. So we're looking on AV, FV, FV, right? This is what we're trying to analyze here. Well, that's going to be the expectation over, well, we said what is going to happen here? The parallel part is going to go with the parallel part, and the perpendicular part with the perpendicular part. This is the expectation of AV, FV parallel, FV parallel plus AV, FV perp, FV perp, right? Because they live in orthogonal spaces. So each one acts differently. Well, the first part, we said FV parallel is always going to be an eigenvector